Nonlinear capacitor. In this example, we'll simulate a disk capacitor that consists of a set of sections connected in parallel. There is a dielectric medium between the plates whose permittivity depends on the electric field strength. The alternating voltage source is connected to the capacitor terminals, and our task is to calculate the current. I believe there would be higher order harmonics in the current wave, so I'm going to use the transient electric model of QuickField to run the analysis. Okay, let's start QuickField now. In QuickField, I create a new problem. Capacitor. Next. Problem type is Transient Electric. Every simulated device is a three-dimensional object, but disk capacitor features rotational symmetry, so I am going to use the two-dimensional axisymmetric model. Length units are millimeters. Next, I'm going to connect the alternating voltage source with the frequency of 50 Hz, so the final integration time would be 0.02 seconds. I will simulate only one period, and the integration time step would be 0.0002. Finish. Here I should draw the Geometer model. I will insert a rectangle with the dimension 0.6 by 24 millimeters. Insert. Close. Zoom to fit. This is a single section of the capacitor, and I need 13 sections more. Right click, duplicate selection, displacement by 0.6 millimeters to the right, 13 copies more. In axisymmetric problems, the axis of rotation is a horizontal one, and I should draw only the upper half of the cross section. So I will switch to insert mode, draw the axis, switch to select objects mode, select, hit delete button, and remove these objects. Okay, now let's assign labels. For labels, we can distinguish one geometric object from another, and we can provide physical properties. Right click and drag to select a group of objects. These are dielectric. This is the odd plate. Hold the Ctrl button pressed to select several objects at the same time. These are odd plates. And these are even plates. Okay, so far these are just text labels. Double-click the label in tree and specify electrical permittivity of the dielectric. In fact, in this dielectric, electric permittivity is a nonlinear function of electric field strength. And here in the text file, I have the dependency, electric field strength, and the permittivity. I will copy these values and paste it here. Here you can see the dependency. Close. Okay. Odd plates would be grounded, 0 electric voltage. And for even plates, I will specify sinusoidal voltage source. The magnitude is 240 volts multiplied by the sine In QuickField, trigonometric functions operate with the degrees. So here I should type in 2 multiplied by p, which is 180 degrees, multiplied by the frequency, which is 50 Hz, and multiplied by time, which is t. Okay. Before I can start the analysis, I should build the fine element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. Okay, let's take a look at the results. Here you can see, let's zoom in, the field lines at some specific moment of time, 0.02 seconds. You can adjust the field picture and switch, for example, the vector of electric field strength. And if I change the moment of time, or I should adjust the scale. Now, if I change the moment of time, you will see that we indeed have the oscillating field. I can show you the time plot. Right-click, time plot, and here you can see the voltage. I can choose another value, time plot curves, field strength. This is the field strength, and let's take a look at the current density. You see the current density is a nonlinear function of time. That's because our dielectric features nonlinear properties. Well, this is the current density, and what is the current? Close, zoom to fit. I will switch off the vectors. To calculate the current, I can use the contour tool. Let's adjust the field picture, switch on the vectors of the current, and adjust the scale. Here is the current. Now to measure the current, I should build the contour. For example, like here. Integrals, reactive current for a given surface. Here it is. Now let's again adjust the field picture and make smaller cell. You see the current is here and here, so I can build the contour this way. And measure the total current in the entire capacitor. Okay, this is the current. You can take a look at the time plot, and you can see the exact values in the timetable. Time and current. You can export the table to the text file, or you can copy these values and paste them in Excel. If you search for the nonlinear capacitor on our website, you will find the example page. Here you can read about the problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and results may be viewed using any QuickField edition including QuickField Student Edition that you can download from our website for free.